Hey there, and welcome back. Today, we're diving deep into automotive history to explore 20 incredibly advanced fuel systems that vanished before the 1980s even ended. These weren't just forgotten ideas, they were revolutionary technologies that pushed boundaries, challenged conventions, and then disappeared into obscurity. If you love automotive history and engineering mysteries, make sure to hit that subscribe button and ring the bell so you don't miss out on more content like this. Let's get started. First up, the electrojector fuel injection system from Bendix. Back in 1957, Chrysler introduced what might have been the first electronic fuel injection system in a production car. The electrojector used transistors and magnetic sensors to calculate fuel delivery, which was absolutely cutting edge for the time. But reliability was a nightmare. The electronics couldn't handle heat, moisture, or vibration. Most cars equipped with this system were retrofitted with carburetors by dealers before customers even drove them off the lot. By 1958, it was gone, and mechanical fuel injection continued dominating the market for decades. Next, let's talk about the Hilborn constant flow fuel injection. This system was a drag racing legend throughout the 50s and 60s. Unlike modern port injection, Hilborn systems sprayed fuel continuously into the intake runners at a constant rate, relying purely on mechanical metering. There were no electronics, no sensors, just beautifully machined aluminum and precise engineering. Racers loved the instant throttle response and raw power delivery. However, as emissions regulations tightened and computer-controlled systems emerged, constant flow injection became obsolete. You couldn't tune it for efficiency or emissions, and by the early 80s, even the die-hard racing community had moved on to better technologies. The Rochester Ramjet fuel injection deserves mention here too. General Motors introduced this mechanical system in 1957 for the Corvette and some high-performance Chevrolet engines. It used a sophisticated arrangement of mechanical linkages and fuel metering units to deliver precise amounts of fuel. The system was expensive to manufacture and required careful tuning, but when set up correctly, it delivered phenomenal performance. The problem was cost and complexity. For the price of one ramjet-equipped engine, you could buy multiple carbureted versions. As performance carburetors improved and became cheaper, the ramjet system faded away by the mid-60s. Moving on, we have the Lucas fuel injection system, used by various British manufacturers. Lucas developed several mechanical injection systems throughout the 60s and 70s, most notably for Triumph and Jaguar models. These systems use sliding metering plates and complex mechanical linkages to control fuel delivery. British engineering at its finest, except Lucas electronics and mechanical systems, had a reputation for unreliability that was unfortunately well earned. Electrical gremlins, fuel leaks, and calibration drift plagued these systems. As Japanese reliability standards raised consumer expectations and Bosch systems proved more dependable, Lucas injection systems vanished from new cars by the early 80s. The Kugelfischer mechanical fuel injection system is a fascinating German innovation. Used primarily by BMW in their high-performance models during the 60s and 70s, this system used a mechanically driven pump with ball bearings, hence the name Kugelfischer, which means ball bearing in German. The system delivered excellent performance and precise metering without any electronics. Racing versions powered numerous championship-winning cars. However, the system was incredibly expensive to produce and required specialized knowledge to service. As electronic fuel injection became reliable and less expensive, even BMW abandoned Kugelfischer in favor of Bosch electronic systems by the late 70s. Now let's discuss the Bosch D-Jetronic system. Wait, you might say Bosch fuel injection survived past the 80s. True, but this specific early system didn't. D-Jetronic appeared in 1967 and used manifold pressure sensors rather than airflow meters to calculate injection duration. It was revolutionary, appearing in everything from Volkswagens to Volvos to Jaguars. However, the system had limitations. The pressure-based calculations weren't as precise as airflow measurement, and the early electronics were still somewhat fragile. Bosch evolved the technology into L-Jetronic with airflow meters, and then K-Jetronic with continuous mechanical injection. The original D-Jetronic was phased out completely by the late 70s, as these superior systems replaced it. The Tech-Element-Jackson variable Venturi carburetor system represents a different approach entirely. Rather than fuel injection, British engineers developed incredibly sophisticated carburetors that could vary their Venturi size to optimize mixture across all operating conditions. These appeared on various British cars through the 70s. The system used vacuum-operated pistons to physically change the carburetor's internal geometry. When working properly, these delivered smooth power and reasonable economy. But the mechanical complexity was staggering, with dozens of small parts that could wear, stick, or leak. Emission controls were nearly impossible to integrate effectively, and the system disappeared as electronic fuel injection proved simpler and more reliable. Continental fuel injection systems powered many aircraft engines but also appeared in some automotive applications during the 40s through 60s. And these systems used engine-driven mechanical pumps and sophisticated metering units originally designed for aviation reliability. Some high-end European cars used Continental systems, and they were known for exceptional build quality and precision. However, they were tremendously expensive and designed for aircraft maintenance schedules, not consumer automotive use. The knowledge base to service them was limited to specialized shops. As mass-market electronic injection emerged, these boutique systems couldn't compete economically and vanished from automotive use entirely. The SU fuel injection system developed by the British company Skinner's Union tried to combine their famous carburetor technology with injection principles. During the 60s, ESU developed a continuous flow injection system using similar principles to their variable Venturi carburetors, but with fuel injection rather than carburation. Several British manufacturers tested these systems. The approach was mechanically elegant, but suffered from the same emissions control problems that doomed sophisticated carburetors. Without electronic control, achieving the precise mixture control needed for catalytic converters was impossible. The system never achieved widespread adoption and was abandoned by the mid-70s. Diesel fuel systems evolved dramatically during this period too, and several advanced designs disappeared. The Lenova air cell combustion system used in various European diesels through the 50s featured a sophisticated pre-combustion chamber design that improved combustion efficiency and reduced noise. Fuel was injected into a small chamber connected to the main cylinder, creating turbulent mixing. This allowed diesels to run smoother than direct injection designs of the era. However, the complexity added cost, and the indirect injection reduced efficiency compared to later, direct injection systems. As diesel technology advanced, Lenova and similar pre-chamber designs were replaced by more efficient approaches. The Napier Nomad aircraft diesel engine used a compound system with both diesel and gasoline fuel systems working together. Though primarily an aircraft engine from the 40s and 50s, the technology influenced automotive thinking about mixed fuel systems. The Nomad used diesel combustion for primary power but added gasoline injection for specific operating conditions. The complexity was mind-boggling, with two complete fuel systems and sophisticated controls. While the engine achieved remarkable efficiency for its era, the mechanical complexity and cost meant the technology never transferred successfully to automotive use. When turbine and jet engines advanced, compound piston engine development ended entirely. Stratified charge combustion systems attempted to use multiple fuel injection stages for cleaner burning. Honda's CVCC system is well known, but earlier American attempts used similar principles with carburetors and auxiliary fuel systems. Ford experimented with systems using both a lean main mixture and a rich pilot charge in a pre-chamber during the 70s. These systems could meet emission standards without catalytic converters, which was attractive when catalyst technology was expensive and unreliable. However, needed the mechanical complexity, maintenance requirements, and eventual reliability of conventional injection with catalytic converters made stratified charge systems commercially unviable. Most disappeared by the early 80s. Water injection systems for both gasoline and diesel engines saw brief automotive use. These systems injected water or water-methanol mixture into the intake or cylinders to reduce combustion temperatures and prevent detonation. This allowed higher compression ratios or boost pressures. Some performance cars and trucks used water injection through the 60s and 70s. Saab famously offered it on turbocharged models. However, the system's added complexity required filling a separate reservoir and could cause engine damage if the water supply ran dry. As engine management systems became sophisticated enough to prevent detonation through ignition timing and fuel control alone, water injection disappeared from production cars. The Wankel rotary engine required unique fuel delivery systems, and several advanced approaches emerged and vanished. Mazda developed various injection and carburetor systems specifically optimized for the Rotary's unusual combustion cycle. Some used multiple injection points per rotor face. Others used staged carburation with different ventures for different operating conditions. The NSURO 80 used a unique injection system calibrated for rotary characteristics. These systems worked but were specific to an engine design that itself nearly disappeared. As Mazda became the only manufacturer pursuing rotary development, most of these varied fuel system approaches were abandoned in favor of standardized solutions adapted from piston engine technology. Vapor phase fuel injection systems attempted to eliminate liquid fuel entirely before injection. Various experimental systems heated gasoline to create fuel vapor, then injected the vapor rather than liquid. The theoretical advantages included better mixture distribution and more complete combustion. Several manufacturers tested these systems during the 50s and 60s. However, the practical challenges were immense. Fuel vapor is far more flammable and dangerous than liquid, creating safety concerns. The heating systems added complexity and energy consumption. Vapor density changes with temperature made metering difficult. Cold starting was problematic. These systems never escaped experimental status and were abandoned as conventional liquid injection improved. Throttle body injection appeared in the 80s, but early versions from the late 70s used fundamentally different approaches that didn't survive. These systems essentially replaced the carburetor with one or two injectors at the throttle body entrance, using electronic control but maintaining the single-point fuel delivery of carburetors. Early versions used continuous injection like mechanical systems rather than pulsed injection. The mixture distribution problems that plagued carburetors affected these systems too. As multi-point port injection became cost-effective, allowing individual cylinder control and better distribution, single-point systems quickly became obsolete. The brief transition technology disappeared almost as quickly as it arrived. Altitude compensating fuel systems represented another evolutionary dead end. Before electronic sensors, some advanced carburetors used barometric capsules that expanded or contracted with altitude changes to adjust fuel mixture. These mechanical systems helped maintain performance at high elevations where thin air would normally cause over-rich mixtures. Some systems were remarkably sophisticated with multiple capsules affecting different circuits. However, they added mechanical complexity and still couldn't match the precision of electronic sensors reading barometric pressure directly. Once engine computers became standard with built-in barometric compensation, these ingenious mechanical solutions became unnecessary and vanished. Turbocharged gasoline engines needed fuel enrichment under boost, and early systems used purely mechanical solutions. Some used boost-referenced fuel pressure regulators that raised fuel pressure proportionally to intake pressure. Others used mechanical linkages from the wastegate or intake manifold to enrichment circuits in the carburetor. These systems worked but required careful calibration and couldn't compensate for other factors like air temperature or exact boost levels. They represented the absolute peak of mechanical fuel system sophistication. Once electronic boost control and injection arrived, allowing precise fuel delivery mapped to exact boost levels and engine conditions, these mechanical enrichment systems disappeared virtually overnight from new applications. Diesel smoke limiting systems used mechanical governors to prevent the operator from adding too much fuel during acceleration. These appeared on many diesels through the 70s and prevented the black smoke that occurs when fuel exceeds available air. The mechanical systems used intake manifold pressure to limit the maximum fuel delivery allowed by the injection pump. Some use sophisticated springs and diaphragms to create different limiting curves for different operating conditions. While effective, these were ultimately band-aids addressing the limitations of mechanical injection pumps. Modern electronic diesel injection eliminates smoke through precise fuel metering and high-pressure injection that ensures complete combustion, making mechanical smoke limiters obsolete. Finally, let's discuss homogeneous charge compression ignition systems that were explored decades before recent renewed interest. Engineers in the 60s and 70s experimented with fuel systems designed to create perfectly mixed lean charges that would auto-ignite from compression alone without spark plugs. These systems used very precise fuel metering and special intake designs to achieve the necessary mixture uniformity. Some experimental engines ran successfully in laboratory conditions. However, controlling the ignition timing was nearly impossible with mechanical systems, leading to rough running or engine damage. The technology required computer control that wouldn't exist for decades. These early HCCI experiments were abandoned until modern electronics made the concept feasible again. So there you have it. 20 incredibly advanced fuel systems that pushed the boundaries of automotive technology but couldn't survive past the 1980s. Each represented brilliant engineering solutions to real problems, but they were ultimately made obsolete by the march of electronics and computer control. These systems prove that automotive history isn't a simple straight line of progress. Sometimes the most sophisticated mechanical solutions get replaced not because they didn't work, but because an entirely different approach proved simpler and more effective. If you enjoyed this deep dive into forgotten automotive technology, don't forget to subscribe and hit that notification bell for more content, exploring the fascinating engineering dead ends and evolutionary branches of automotive history. Thanks for watching, and I'll see you in the next one. What's really fascinating when you think about all these systems together is how they reveal the fundamental challenge that automotive engineers faced during that transition period. These weren't failures of imagination or engineering skill. The people who designed the Kugelfischer system or the Lucas injection setups were incredibly talented, often producing work that was ahead of its time in many ways. The real issue was that they were trying to solve electronic problems with purely mechanical solutions, or mechanical solutions to problems that really needed electronics to address properly. It's like trying to write a novel with a typewriter when you're imagining what a word processor could do. The tool just doesn't match the task perfectly, even if you can make it work with enough ingenuity and precision. The transition to electronic fuel injection in the 80s wasn't really about any single breakthrough in fuel delivery science. Instead, it was about the cost of computers finally dropping enough that it made economic sense to put a microprocessor on every car. Once that happened, suddenly all those clever mechanical solutions became expensive complications rather than elegant simplicity. A computer could monitor oxygen sensors, barometric pressure, coolant temperature, intake air temperature, engine speed, throttle position, and a dozen other parameters simultaneously, making decisions thousands of times per second. No mechanical system, no matter how sophisticated, could compete with that level of real-time analysis and adjustment. It's a perfect example of how technology revolutions rarely happen, because one thing gets better. They happen when the enabling technology becomes cheap and reliable enough that it transforms what becomes economically viable. Another pattern you'll notice across all these systems is the relationship between regulation and technology. Almost every one of these disappeared either because emissions regulations made them unworkable or because new regulations made computerized solutions mandatory. The mechanical fuel systems of the 50s and 60s were actually quite good for their era, but catalytic converters required precise mixture control that mechanical systems simply couldn't provide reliably enough. Water injection was great for performance but couldn't meet noise or safety regulations. Stratified charge systems could pass emissions tests without catalysts, but once catalytic converter reliability improved and costs dropped, the simpler approach with CATs and electronic fuel injection won out. Regulation doesn't necessarily drive innovation toward what's best, but rather toward what's cheapest while meeting minimum standards. Sometimes that happens to align with the most elegant solution, and sometimes it doesn't. It's also worth considering what these systems tell us about the future. We're at another transitional moment right now with electric vehicles and hybrid powertrains. In 50 years, someone might be making a video about all the sophisticated hybrid systems and dual fuel approaches that vanished because either pure electric vehicles became practical or because some entirely different technology replaced them. Or maybe they'll be discussing fuel cells and hydrogen systems that seemed so promising in the early 21st century but didn't survive into mainstream production. The technologies that seem cutting edge and sophisticated today often don't make it to mass adoption. It's humbling to think about, especially if you're passionate about mechanical engineering or innovative solutions. Sometimes being brilliant and innovative just isn't enough if economic forces push the market in a different direction. The human cost of these transitions is interesting too, though often overlooked. All those specialists who could perfectly calibrate a Hilborn fuel system or service a Kugelfischer injection setup suddenly found their expertise worthless as those systems disappeared. Or the small shops that could rebuild Rochester ramjet systems had to completely retrain or go out of business. The knowledge wasn't just lost from the machines, it was lost from the people who possessed it, because there was no longer any economic incentive to maintain that skill base. That's part of why restoring classic cars with these systems today is so challenging. Even if you find the right parts, finding someone who actually understands how to properly tune and maintain them is incredibly difficult. The institutional knowledge simply evaporated. This also raises an interesting question about whether we're losing something important as we move toward increasingly computerized systems. There's real value in understanding how a mechanical system works, in being able to see the cause and effect relationship between a change you make and how the engine responds. The drivers and mechanics of the 50s and 60s could develop an intuitive understanding of their cars because the systems were mechanically transparent. You could see how adjusting a carburetor jet affected mixture, watch how a fuel pump pressure regulator responded to load changes, understand the mechanical linkages that connected your throttle input to the fuel delivery. Modern systems work better and more precisely, but that transparency is gone. You can't intuitively tune a modern fuel system because it's controlled by algorithms you can't see. That might not matter much for most people, but it represents a loss of a certain kind of understanding and connection to the machinery that we drive. And beyond the technical aspects, there's something almost poignant about looking at these abandoned systems. They represent enormous amounts of engineering time and resources invested in solutions that ultimately went nowhere. Think about how many engineers worked on perfecting the electrojector system, or developing the various Lucas fuel injection approaches, or optimizing Lanova combustion chambers. They were solving real problems, making genuine improvements, contributing to the overall advancement of automotive technology. But from the perspective of history, most of that work is forgotten, considered a dead end that contributes nothing to modern engineering. It's a reminder that progress isn't always a neat accumulation of improvements, where each generation builds directly on the last. Sometimes entire branches of development are pruned away, not because they were bad ideas, but because the overall trajectory of technology shifted in a different direction. There's also a cautionary tale here about specialization and standardization. The variety of fuel system approaches in the 50s through 70s created a fragmented landscape where knowledge wasn't transferable, and manufacturing couldn't benefit from economies of scale. Once electronic fuel injection became standard, suddenly every manufacturer could use variations of the same basic technology, allowing components to be developed more efficiently and knowledge to accumulate across the industry. Standardization has real benefits for cost, reliability, and the speed of overall progress, but it also means that diversity of approaches gets eliminated. Some ideas that might have been viable might never be fully explored because the industry has already chosen a different standard. The market forces don't necessarily select the best solution, just the solution that achieves critical mass first. If you've made it this far, you probably share the same fascination with automotive history and engineering dead ends that drives content like this. There really is something compelling about understanding not just what succeeded, but what failed and why. It gives you insight into how technology actually develops in the real world, messy and contingent, and driven by economics and politics as much as pure engineering merit. These forgotten fuel systems are little windows into that process, showing us how brilliant solutions sometimes can't survive the broader forces shaping technological change. Whether you're interested in cars, engineering history, technology adoption, or just curious about how the world got to where it is today, these stories are worth knowing. They remind us that the path we're on isn't inevitable, just the one we happen to take. Make sure you're subscribed so you don't miss more explorations into these fascinating branches of history that didn't quite make it to the modern era.